Alright, today we're going to talk about electromagnetism. So this is PS11, electricity, and we're going to focus in on the relationship between a magnetic field and electric current. And we're also going to talk about electromagnets, motors, generators, and how we can use them. So that's our main idea for today. And so the first thing I want to talk about is, earlier today we made the Ørsted model with the compass, and what happened is in 1820 this Danish physicist, Hans Christian Ørsted, observed a magnet move in the presence of an electric current or field. So Ørsted hypothesized that electric current had produced a magnetic field, and his later experiments confirmed this hypothesis. So the real big thing here is, going back to the main idea is that electric current can produce a magnetic field. Okay, and electromagnetism, write this down on your paper, okay, results when electric currents and magnetic fields interact with each other. Okay, so that's what electromagnetism is, and it's based off of the principles of electromagnets and electricity. So how can we make a magnet using current? Well, one way we can make it is we take a coil wire that carries an electric current, okay, and produces a magnetic field because of that coil wire, just like with our compass. Okay, and that's called a solenoid. The more loops, the stronger the magnetic field is. So if I put a piece of metal inside this loop and then connect one side of the wire to the other side of the wire, this will produce a strong magnetic field, and actually that iron, if it's a nail or whatever, will align all the domains to pick up different objects. So here's a good picture right here. So when you put that solenoid in there, okay, and you put the current through the loops of wire, you get a magnetic field and like the pins stick to it. So wrapping a solenoid around the iron core makes an electromagnet, which combines the magnetic field of the solenoid with the magnetic field of the iron core. So once again, if I add more loops, I increase the electric current, the electromagnet gets even stronger. Okay. So let's talk about some uses for electromagnets. Okay, there's plenty of uses in our world. We use these all the time. Everything from the doorbells in your house to trains to motors to whatever our modern everyday life uses, somehow electromagnets are involved. So they're used a lot of times. The traditional one is used for lifting and moving large metal objects containing iron. So in a junkyard, this usually happens a lot, where we use a electromagnet, okay, to lift up the heavy cars and then put them somewhere. It's a lot easier than just taking it with a crane or trying to attach a forklift or something. So it creates that magnetic field and attracts the metal objects. Turning off the current turns off the magnetic field. Those domains start to go random again. When I turn them back on, the domains line up in the iron nail, okay, and it becomes magnetized again. Now, if you get a really powerful electromagnet, it can raise maglev trains above its track, just as poles of a bar of a magnet can repel each other. Okay, we talked earlier about how North Pole and North Pole repels, South Pole and South Pole repels. Okay. So that's kind of the idea. In Japan, they're doing this right now, currently. Okay. So MRIs, okay, those are the machines that are used for looking inside of your body and looking inside your brains and your heads and stuff like that. Those are powerful electromagnets, okay, and they use electromagnets in radio waves that produce a detailed image of whatever's inside. So doctors use that to scan and diagnose different ailments and things like broken bones, strained tendons, things like that. Okay. All right. Continuing, this right here is a galvanometer. I have one I showed you earlier. Galvanometer is a meter that measures the strength and the direction of a current flow in a current of wire. So a galvanometer contains an electromagnet between two poles. So there's your electromagnet. And when the current is applied to the electromagnet, the two magnetic fields interact and cause the electromagnet to turn. Okay, so right there is kind of the idea. Here you have your magnet, you have your coil wire, and then what happens is when you apply current, it'll either turn one way or the other way. And that indicator attached will tell me the strength of and the direction of the current. So let's go into motors. We're going to look at motors a little bit later this week. An electric motor changes electric energy into mechanical energy. Okay? So that's what you need about electric motors. It takes electrical energy and makes it mechanical. Okay? So we use electric motors in various sizes, from large motors used for powerful Ferris wheels to small motors used in computers, cooling fans, in your phone, a little vibrator that like I said, the phones in your have the little motors in there, the little vibrators, all the way to in your cars. A hybrid car has electric motors. So we use motors in everything. Okay. So a simple motor is just a coil or loop of wire called an armature. So there's your little tiny, and it's a very simple one. Loop of wire called an armature. Okay, and it's mounted between two poles, the North Pole and the South Pole. Okay, and the armature becomes an electromagnet when a current passes through it. So you can see the current, right? Electromagnet. We talked about loops of wire. And as it rotates, the poles will either push it away or pull it by the opposite poles of the magnet. And the armature will turn until its north pole is opposite of the magnet's south pole. So this little device here is a communicator and reverses the direction. So once it goes around, it reverses directions and it can make a complete turn. And it can keep doing this. So we're going to build our own motors later on this week. Okay? So electric motors are very similar to galvanometers. However, in a motor, okay, the electromagnet is made to rotate all the way around. Okay? Remember, we're taking electrical energy and turning it to mechanical energy. Okay? So the other thing we have here is like electromagnetic induction. So using a magnetic field to create electric current in a wire is called electromagnetic induction. So we can actually reverse that. Instead of taking electric current and making something move, we can take something that moves and make an electric current. So when an electric current charge moves through a wire, the wire carries a current. Magnetic force from the magnet moves inside the coil of wire and makes electric charges in the wire move. When the magnet stops moving inside the coil, the electric current stops. So instead of moving the armature around inside of a magnet, this time we're moving the magnet inside of a coil wire, and that will produce that'll make that electric current. Okay. So here's an example right here. Okay, so we have the coil wire. Okay, you have the magnet inside, and as I move the magnet back and forth, you'll see over there the galvanometer is actually moving. So when you move it, and the faster you move it, the stronger the current. Okay. And so we're inducing a current. We're inducing the electrons moving because of that magnetic field. So here's some other uses for induction. So the transformers on your telephone poles or inside of your phone chargers, they can be really small, they can be really large. So transformers either increase or decrease the voltage of AC or alternating current. So in the power lines, we want to decrease because those lines are 7,000 volts, and we want to bring them down to about 120, 200 volts to go in your house. Otherwise, everything would fry and everything wouldn't work in your house. Most transformers are iron rings with two coils of wire. The current is primarily in the side makes an electromagnet because the current alternates the magnetic field charges. Okay, so the current comes in, and then whatever comes out is usually less, or I can reverse it and make it more. The little power packs on our computers are also transformers. Okay, and I think I'm going to show you one of those as well. Okay. So here we go, step-up transformers. So in a step-up transformer, okay, there are more turns of wire in the secondary side, and in a step-down transformer, there's more turns of wire in the primary side. So here's a step-up one. Okay, so less coils here, and then over here there's more. So step up, lower voltage, higher voltage. Over here we're going to step down. More coils, okay, over here, less coils. So we're stepping it down. The voltage is going down in this one. So we use electromagnetic induction to make mechanical energy into electrical energy. So this is what we do in power plants. Mechanical energy is used. We rotate the turbines. Okay, so we use a coal. We heat the coal, boils the water. So the power plants use that steam, turns the turbine, and then turns the generator. The generator makes an electric current and sends off to your house. Okay, we can do this by the old-fashioned coal plant, which is a lot of power. You can do it by windmills. You can do it by falling water, which is hydroelectric, even ocean waves. So you can make your simple generator as well out of this little box. Some people have already made their generators there. Okay, we have a hand crank generator you guys will get to see. And generators are used to induce current when magnetic moves in the coil wire and when wires move between the poles of magnetic field. So in a simple generator, a wire loop at the end of a rod moves through the magnetic field of a magnet. In the first half of the turn, one side of the loop moves downward and then upward and back downward. Second half, back downward. So this is going to create an alternating current. Okay, so that's how it works. Okay. So we're going to build some motors in not today, but on the second day. The first day you'll be building an electromagnet. The second day you'll build an electric motor.